and say a few words about how she actually ended up here in Hawaii. Laurie was born in Colorado and then did her undergraduate work at Northern Arizona University. I'm showing two pictures here of that phase in her life. Laurie leaning against what she assures me is the old a telescope that Northern Arizona University used. They got a better one for her to do her undergraduate work on. And Laurie in front of meteor crater. Is that an early indication of your interest in comets and things that might potentially fall down on us? But things got really interesting. In 2010, when Laurie was one of our RU students at the IFA, we see her here in front of the scenery of Mauna Kea telescopes. Now that's pretty standard for RU students. Less standard is that she also met Jason there at that occasion, precisely 2 days short of 10 years today. So yeah, the two met at the IFA and married then 5 years later. But on the right, you see Jason and Laurie upon her graduation from Northern Arizona University. In between, the RU project was quite successful, and I think started Laurie out on interest in everything related to young stars, formation of stars, protoplanetary disks, ices, comets, that range of topics here. Her advisor for the RU was Adam Krause at the time at the IFA. And then, finally, then she decided to actually join our graduate program. These are just two images from the first year there when she joined. The welcome party for our incoming graduate students on the left, and the reception that Karen Meach held somewhere on the windward side, apparently, with 3 of our graduate students in medieval attire. This is not the standard attire for our graduate students, but it was the theme of that party. And from there on, then, Laurie started out working with me on the project related to our long involvement in the James Webb Space Telescope. For me, it has been more than 20 years now, the involvement in that project. And her work is related to preparatory, ground-based scientific work on the field of studies of ices in nearby molecular clouds. And with that, I hand it over to you, Laurie. I need to stop sharing here. Okay.
Great. And now I have to start sharing. Share screen. All right, I'm going to take the mask off. You guys are a nice safe distance away for now. Great. I hope everyone can hear me. There we go. Point the microphone. Thank you very much, Klaus, for that great introduction. It was nice to kind of relive some of those moments again. So I'm very excited to be here today to share with you all of the work that I've been doing here in Hawaii, at the University of Hawaii, the Institute for Astronomy, under Klaus Hodap. So working in Hawaii had some of its challenges. I guess there's a little lag here. So it had some challenges. There were hurricanes. Some were definitely worse than others. Oops. Trying to get my mouse here to show stuff. It's a little slow. Okay, so there were some that were a little worse than others. We had ballistic missile threats. This was actually the text message that I received on my phone back in January of 2018. And we even had volcanic eruptions, which came with its fair share of earthquakes. So I think it's only fitting that it's finishing during a pandemic. And even in Hawaii, we're not exactly the safest here. But luckily, being in Hawaii had many advantages. I was able to observe on many of the telescopes here. As shown in the upper right, you can see me at the Subaru. In the bottom right, I was on Haleakala. I was able to participate in a lot of outreach events. So it was really great, but there were also a lot of non-work related things that were a lot of fun, such as dancing hula and tap, and even getting engaged to my now husband. So today I want to talk to you about very small components of the universe. I'm looking at ice and dust. So not huge, big galaxies, nothing that's going to be very, large. I'm looking at the very small things. And so you might be wondering, well, what is a girl doing in Hawaii in tropical paradise why is she talking about ice? So I'm going to try this video and hold it up to my speaker here and hope that it works. Oops. I might get feedback that way. Oh, well, I'll just skip it. So what you might, let me turn my volume down again. There we go. Sorry, little technical difficulties here. But so actually, you might sit there and say, well, you've been in Hawaii. Why are you going to talk about ice? As Klaus mentioned, I actually grew up in Colorado, and so ice was around me all of the time in the form of snow. And even when I went to Northern Arizona University, there was also a lot of snow, as you can see here in the bottom left corner. So what do you think of when you hear the word ice? Possibly you think of winter sports such as bobsledding or ice skating, or maybe you think of my favorite animal, penguins. But actually, now after doing this work, I think of ice more in the context of space. So there's ice on planets such as Mars or the moons of different planets. We know there's ice on Pluto. There's even ice on our own moon in some of the darkest craters. And comets are also a very prominent place that we can see ice in the universe. And down here in the bottom, this is also a cloud in space that is also showing where ice can actually form.
Can you turn on your camera? They cannot see you.
My camera. Yeah. Oh, okay. It says unable to start video. I can't start video because the host has stopped it. All right, so I'll just keep going and we'll try and work out the video so that you can see me, I guess. So we want to know, where do ices actually come from? And so in a dark cloud in space made up of dust and gas, you'll start to develop these small dense cores within these kind of larger clouds. And so it's maybe a little hard to see on this projector here, but hopefully you can see it on your computers. And so you get these very dense cores that start to form, and because it's shielding from a lot of outer radiation, any interstellar radiation, the center gets very cold in the core. And so you can actually start to take the gases and condense them down onto dust grains in the form of ice. And now it's not going to the next slide. Let me see if I can start my video now. Nope. Okay, well, it appears to be sort of frozen. Okay, I will skip ahead. Sorry for this. Okay, there we go. So then the next stage of this evolution, you actually have these clouds that are sort of in an equilibrium where they're just sort of sitting out there in space, nice and quiescent. But then for different reasons, you can actually start to have a gravitational collapse of this molecular cloud. I call it a molecular cloud because it's made up of mostly molecular hydrogen. And so once you start to get this collapse, it gets very dense in the center of the core. And as it gets very dense, that means that there's still a lot of dust and gas that's shielding the very inner parts of the core from any interstellar radiation. And so again, it gets very cold, and you'll actually start to see dust grains form icy mantles on the outside. And these icy mantles that form actually also allow grains to start sticking together, which is very important for us to understand because that could lead to building things such as planets. So I want to go through this ice formation process a little bit. So what happens is when the temperature is still above 20 Kelvin or so, you'll have this little dust grain, and you start to condense down the polar ices. So polar ices are ices that have a high dipole moment. And so those are things like water and carbon dioxide, but then you still have a lot of gases in this system. But then as it gets colder and the cloud becomes more dense, you start to freeze out other molecules, such as carbon monoxide. So those are more apolar ices. And then further along, as you get to even colder and denser regions, you start to form things such as methanol, which is this CH3OH here, and formaldehyde. And you can also notice that these grains have also started to be able to stick together. I'm still not able to share my screen, or share my video. Okay. So in this process, and I guess whenever I touch anything outside of the PowerPoint, I lose control of it. Very sorry for the technical difficulties here. Okay, I have to stop sharing again. Stop share. Okay. All right, so as I was saying, this is where your temperature is decreasing, and so this is where the ices are starting to form, and the density is increasing. And so then what happens at the next stage? Well, a star actually can start to form in the core. And so once this star has started to form under enough density, then you start to see a disk that develops around the star, and it's still embedded inside of an envelope, and you'll also start to see some of these bipolar outflows. Later on in the cycle, you'll start to see that the envelope starts to disappear. And so during this phase, this is kind of what we think is happening to these dust grains. So it's getting warm, and so the actual, it's called a distillation phase, where some of the apolar ices start to sublimate. And then later on, you get sort of a segregation phase. This is a little bit warmer, when the water is starting to crystallize, and you start to kind of see some of these different molecules sort of separate. And finally, in the energetic phase, you're kind of getting rid of all of these ices again, because they've sublimated off, but you are left over with some residue, things like organic molecules and salts. So this particular process is when the temperature is increasing after the star has already formed. And so I mentioned organic molecules. Well, I want to go through and tell you a little bit what these organic molecules are and why they're important. So these are made up of carbon atoms in rings or long chains that are attached to other molecules such as hydrogen, oxygen, and nitrogen. And so you might be familiar with some of these, like caffeine or aspirin. But organics are actually what really makes up life. So your dog or your cat or your pet penguin is all made up of organic material. And so if you break down life into things like carbohydrates and proteins, and you break that down even further into things like sugars and amino acids, and then further down, you are essentially making all of those up with organic molecules. And so how do we actually get organic material? Well, in this cold, a star has not formed yet, you start to actually see this methanol ice, which could be a key component to forming more organic material. However, also in this energetic phase, when it's warm, you could also be forming organics. However, we don't really know which process it's going in the actual universe. And so we can do laboratory measurements to see, how these organic material can form. So, for example, we can go into the laboratory and create ice in a vacuum chamber and then irradiate it with high energy photons. And then the original volatile ices will start to sublimate, and what's left is a residue that's made up of complex organic material. So can organic material actually form without high energy processes? Well, there was a different study that basically said, well, let's take just regular carbon monoxide molecules and let's try and just add hydrogen to it, but in cold temperatures. So you add hydrogen and you start to get things like methanol and formaldehyde. And once you do that, you start to get this wide range of complex organic molecules. So this would imply that maybe this stage can happen before a star has even formed, and there's no need for energetic processes. So there's a lot of studies that show that this methanol ice is a good basis for complex organic molecule growth. And so it's very important for us to study where this methanol ice is. So then what happens to this ice and organic material after the star has just been formed? Well, the next stage in the process is usually with something that looks like a debris disk. So interesting fact is that's actually what I studied as an undergraduate. So debris disks are a later stage in the star's evolution. Planets have just started forming, and they're still trying to work out where they want to be in the solar system. And so there might be some collisions, there's different dust and everything that's kind of moving around. And in our own solar system, when our star was only about 600 million years old, we had what's called the late heavy bombardment, which could have possibly produced something that looks like a debris disk. And then later on, you start to get a young stellar system that looks very similar to what we see in our own solar system today. So did some of that organic material end up on the Earth? Or did some of it actually just kind of dissipate out into the emptiness of space, never to be seen again? Well, we actually know that some of this material was trapped up in comets. And so comets are remnants of the early solar system. These were things that were formed at the very earliest stages of the solar system. They're made up of very porous, fluffy dust, particles, and ice. So what happens is as the comets come closer to the sun, you can have this layer of ice that pushes off some of the dust, and you get these beautiful tails as seen in some of these pictures here. And so these outbursts of activity actually allow us to understand some of the composition of these comets. And so there was a mission called the Rosetta mission that visited a comet, 67P. You might remember some of the press releases as it looks kind of like a rubber duck. But they found that nearly half of this, the dust collected has organic molecules, and it's the most carbon-rich body known in the solar system. So if you look at this figure here on the right, you can actually see the amount of carbon is very similar in 67P to what is found from the earliest stages of the sun. And so it's great. We would love to go to every comet and collect material and see exactly what kinds of ices and dust were present so that we can get a really good census of what was around at the early solar system. But that gets very expensive. And so what we need to do is monitor activity in a large sample of comets over time from the ground. And this picture is me in front of the Pan-STARRS telescope, which is actually a great telescope for discovering some of these comets. And so we want to know what happens for the life of a comet. So comets can change drastically on short time scales. As you can see in this picture here at the bottom, this is in October and then January and March, and you can see wildly how much this comet can change. And so we want to understand what happens to the ice over the lifetime of a comet. So what happens to the primitive ice through this lifetime, and then what happens at the end? Do comets just like break up catastrophically, or do they just slowly lose their volatiles over time and turn more into an asteroid-like state? So one way that I was able to kind of look into this process was by studying a low-activity comet, 49P Erin-Dragos, which has now become my favorite comet. Now you might be saying, well, it's low activity. It doesn't produce these beautiful wild tails. Why is it so interesting? Well, it's interesting because we can actually understand a little bit about what might be happening at the end of a comet's life, because it's been hypothesized that it might be actually dying. But in 1992, we saw this nice little tail coming off of 49P. And then in 2004, there was this nice narrow feature. And then in 2012, we saw both a tail feature and a jet-like feature coming towards the bottom. And so we said, well, is it a dying comet? It kind of looks like it might be becoming more active. And so we were able to take a time series of some observations in 2012 to kind of look at the shape of this cometary tail. And so we saw in February that it was producing this nice tail. About a month later is when we saw the tail in the horizontal direction and the jet in more of the vertical direction. And then only a few days later, we could still see the tail, and the jet, hopefully my mouse is following here, the jet is a little bit more disconnected from the comet nucleus. And then only 2 weeks later, you can barely see the tail, and there's really no jet-like feature. And these bright areas right here, that's just a poor subtraction of a bright background star. So that's not part of the comet itself. So what I was able to do was use FINSON-PROBSTEIN dust models. And this allows us to look at what the grain sizes are coming off of the comet, the distribution of those grains, and when the activity peaked and how long it lasted, and what the grain velocity was. So here again, I've showed you the observations that we took, and using these models, I'm able to reproduce these different features that we saw for the comet quite well, and in fact so well that when you look at the residuals, you can barely see anything left from the tail itself. And so what we found is that in 1992 and in 2012, the tail-like feature had large grains, it was a long duration event, and the peak activity was near perihelion. Perihelion is the closest approach to the sun. However, in 2004, that feature was a lot more similar to the jet-like feature that we saw in 2012, with small grains, and it was a much shorter duration event. And so what we can use those models for is to take some of the outputs and use them to make ice sublimation models. So these models allow us to understand how active the surface of the comet is and what ices are actually driving the activity on this comet. So I will try and walk through this slide here. So what we have here are 6 different apparitions. So that's the different times that the comet came around the sun. It has a period of just over 6.5 years. And so what we see here on the bottom is true anomaly, where 0 represents when the comet is closest to the sun. And coming from the left towards 0, that represents the comet coming in towards the sun, and then after that it's going away from the sun. And on the y-axis here, I have the R magnitude, so just the magnitude in the R band. And the red points represent the photometry I have in my sample. The green represent photometry from the literature, and the turquoise points represent photometry from the Minor Planetary Center, which are reported by other astronomers. And so if we wanted to model what the comet should look like, if it was just a bare nucleus, it had no ice coming off of it, and it just looked like an asteroid essentially, then this is the model that we would get. And so you can see at the further away from 0, the model fits pretty well, and you would kind of expect that because these are very cold temperatures, and so you're not really going to get ice sublimating off. However, when you get closer to the sun, you'll actually start to see that some of these points don't really quite fit anymore. And so we need to introduce some sort of ice that's sublimating. Well, we introduce water, which has been seen for comets a lot, and it actually starts to fit this data really well. If you look at some of these red points, it's actually fitting pretty decently. But what about these turquoise points? It doesn't seem to be fitting those. And so if we introduce carbon dioxide as another ice that's driving activity, we get a great fit. But the only thing is carbon dioxide should have sublimated further out from the sun because it can sublimate at colder temperatures. And so why is it that as it gets close to the sun, that all of a sudden it's being part of the activity? Well, what we think is happening is, some of the water starts to sublimate off, and then it reveals lower levels of ice below the surface that have carbon dioxide. And so then all of a sudden carbon dioxide is free to go, and it starts to push off plenty of dust and drive some of the activity. And so what we can actually do is look at how much of the surface area is actually active over time. And so we see that in the first apparition, we had about 3% of the surface area was active, but by the fifth apparition, only 2.2% of the surface area was active, in only about a 30-year time frame. So we definitely need to continue monitoring 49P and other comets like this to provide more insight to the end of a comet's life, because perhaps, the next time it comes around, it will be wildly active, and this is maybe just a quiet time in its life. And maybe by the next time it comes around, there will be a new layer of ice that's revealed, and it will become active again. So it's very interesting, though, because this could be one of the first cases where we're witnessing a comet transitioning into a more dormant state. And so, but we still don't know really what conditions are required for different ices to form. And we also don't really know how much ice there was before the solar system formed. So what we do need to do is we need to look outside of our solar system to see where that ice is actually forming currently. And so the way that we can do that is by studying molecular clouds, and particularly molecular cores. I might use those a little interchangeably. Molecular cores are just very small, dense parts, and molecular clouds are kind of usually thought of as being larger. So my sample has molecular cores, and they're made up of mostly molecular hydrogen in the gas phase. But what we can do is we can actually study lines of sight through these clouds to get information on where the ices have formed. And so how do we actually understand what's happening through inside of the cloud? Well, if we have a background star that can illuminate sort of the line of sight through the cloud, we can say, well, we know a little bit about what the star should look like. If we subtract off the spectra of the star, we should be left with a spectra inside of a molecular core, which could reveal ices. And so we want to know what kind of different densities of dust within the cloud may reveal different ice abundances and identify thresholds where ices can form. So this particular source is actually a background star. It looks like it might be in front of the cloud, but this is actually an infrared image, which I'll go into a little bit later. But as you go to longer and longer wavelengths, you actually start to see more stars through the cloud. And so this is actually a great target, and one of my targets that I will be using as a background star to sample along a line of sight to see what ices are in the molecular cores. So when we take a spectrum and subtract off anything that's related to the star itself, you'll be left with something that looks like this, that's representing what's happening inside of a molecular core. And so I'm not going to be talking about some of this stuff on the right, but I will be talking about water, carbon monoxide, and methanol ice. And just as a reminder, methanol ice is important as something that could lead to organic material and thus life. And so I have a sample of 14 background stars or young stellar objects, or YSOs, as I will be referring to them to. And so in the green circles here are background stars to different clouds, and the red represent YSOs. The blue are also YSOs, but those are not part of my sample. And so you'll actually see here on the right and the bottom left, those are actually stars that have already started to form in this core. So some of these cores have already formed a star, some of them have not. So this one on the bottom right has not formed any sort of star. So this is at an earlier evolutionary stage. And so when we take the spectrum of a background star, this is sort of what we would get. We have the black line representing the stellar spectrum that I observe using the IRTF telescope. And then the red represents a model spectrum using a stellar library of spectral templates. And so we actually find for this particular star, it resembles an M2 giant star. And so you can see here on the left, there's these what's called the CO band heads. So we're actually matching that quite well. And then we're also able to model the water ice feature and the carbon monoxide ice feature over here on the right. And we even see this methanol ice feature here as well. The model does not quite fit this region that well, just because there could be scattering due to large grains and possibly ammonia ice in that band as well. And so what we can then do is turn this into something called the optical depth. And that's sort of the ratio of the mean free path of a photon over the thickness of the cloud. And this can vary by wavelength depending on the density of different molecules within the cloud. So for example here, the optical depth is 0, but then you get a huge optical depth, which is representative of the water ice feature in this particular cloud. So the optical depth is great because it then allows us to calculate something called the column density. And the column density is just the number of molecules per centimeter squared. So as you're looking through the line of sight, how many molecules are there per centimeter squared? And you can actually see a little bit better this methanol ice feature pop out in this kind of plot. And this is actually after I've already subtracted all of the features that come from the star. So it doesn't look as messy as this. It starts to look very clean where we can see some of these ice features popping out. And so I'll go into that methanol ice a little bit more. We actually were able to detect two particular background stars that had methanol ice along the line of sight. And so what happens, just to kind of go back to the beginning, what happens is that the carbon monoxide undergoes nearly a complete freeze out. So this is at very low temperatures and very high densities. And so because most of the carbon monoxide is in the frozen solid state, there's not as much left in the gas state. And so that means that the hydrogen in the gas state is more than the carbon monoxide in the gas state. And so with more hydrogen around, you can start to get hydrogenation of those CO molecules, which leads to creating things like methanol ice on short time scales. And so this is really great because this could be a way that we're starting to get the onset of complex organic molecules. And so my study was actually the first study to measure the carbon monoxide and methanol ices toward background stars instead of using YSO envelopes. And so we've already known that this methanol ice can form in the envelope of a YSO, but we want to know, can it form before that stage? And so what we find here is the spectrum of just the CO feature. And if we had just pure CO, you would see just this yellow curve here. However, you see that the spectrum, which is shown in black, doesn't quite fit this yellow curve. And you actually need to introduce this red wing here. And that red wing is indicating that there's actually a mixture with methanol ice. Now it's cool because this particular source is in a collapsing cloud, so there is not a young star in this system at all. So we're seeing this methanol ice early on, and it seems to be that this formation is well underway before a star forms. And so then what I've done is I looked at the ratio of this methanol ice, the pure detection that we saw, and compared it to this wing that we were able to see. And so I get these ratios here, and I can compare that to what we see in YSO envelopes. And you can actually tell that the ratio of our two sources can match what we see for low mass class 1 YSOs. So this is the class 0 stage YSOs is the earliest stage of YSOs, and then it goes to class 1, class 2. And so it looks like that the amount of methanol ice that we actually have at this early stage before a star has formed even makes up the amount of methanol ice that we see at later stages. So possibly the methanol ice that we're observing at a later stage where there's already a YSO was already formed well before that star was born. However, you also see that there's a class 0 star, and that ratio is much higher than what we're seeing. So it's possible that some of the methanol ice is formed early on, and it continues during this earliest stage of a low mass star forming stage. But this is only one data point that we have. for the low mass class 0 sources. So we definitely don't know exactly what's happening at that stage, but we do know that we have a lot of methanol ice and even more than some low mass YSOs in our sample, even without a YSO. And so I'll come back to this into how do we get this organic material? Can we form it in a cold environment, or must it be in a warm environment like around a YSO? Well, it turns out it can happen in the cold environment. Methanol ice is actually abundant with respect to carbon monoxide and exists mainly as a methanol-rich carbon monoxide ice layer. And so the warm phase, well, it could still happen there, but we definitely know that it can happen in the cold stage. So where is this methanol ice in relationship to the highest density area of the molecular core? Well, you can see in this figure here, I've pointed out the lines of sight that we were able to detect methanol ice. So there's this one here, and we have this one over here on the right. And so this one on the right actually has a young star in the center of this white circle. And that is indicating that this methanol ice is outside of the YSO envelope for that particular cloud. And I've also shown here the white circle just represents sort of the distance to the Oort cloud in our own solar system, which is where we actually get comets from. So it's just kind of a nice scale to see this. So we see that these two lines of sight show 30% of carbon monoxide ice is mixed with methanol ice, but a very small amount of the carbon monoxide is frozen out. So we want to know what fraction of the cloud is dense enough for the ices to actually form. So what we can do is actually look through lines of sight through the entire cloud, not just my 14 that I had before, which is nice, but we would really like to know about the dust properties in these clouds and what's happening overall. And so the ice formation actually depends on the density and how much shielding there is from the interstellar radiation. Because if you have a star sitting here in the middle here, our background star, and you want to know what's happening along that line of sight, well, you want to know how close it is to the edge of the core, because that could help with shielding from interstellar radiation. But you also want to know how dense it is in that region and how close it is to the densest parts of the core. So we want to know where that ice is in relationship to both. And then also compare the conditions at different evolutionary stages. What I can use is a tool called extinction mapping. So extinction is just the amount of light that is absorbed of a background target by something intervening like a cloud or a molecular cloud. And so at longer wavelengths, as you can see in this figure below, at longer wavelengths, you start to see more and more stars in the background as stars become less extincted. And so this was recognized, and there was a method called NICE, which is the near infrared color excess, which basically was able to calculate the extinction based on this knowledge. And so I'll walk through this equation a little bit here. If you were to measure a star in the H band and then the K band, you would get an H minus K color. And then let's say you know something about the intrinsic color of these stars. And then using an extinction law, you can actually get the extinction at a particular wavelength. So for example, what's often used is the visual V band. And so that intrinsic color, you go, well, how do we know what the intrinsic color is? Well, the benefit to using NICE with the H and K bands is that in H minus K, if you have an A0 star or an M0 star, the intrinsic color only changes by about 0.0 or by 0.3. And so you're not introducing a huge amount of error. However, what the next method was the NICER, which was the NICE revisited method, which generalizes NICE to extend to multiple wavelengths. So that means that if you only had J and H, you could still produce an extinction, or if you had longer wavelengths, you could still produce an extinction. And so let's go back to how we get the intrinsic color of background stars. Well, one way you could do it is you could take the spectrum of every single star in your field. That gets extremely expensive on telescope time, and it's very difficult to do, and so that's not exactly the best way to go about it. You could use a field where the background stars are of a similar spectral type, which means that they would have similar colors. And so if you have a cloud with the background of the galactic bulge, then you would have mostly late K and M stars. So that also already, if you look at this figure here, if you're only looking at the K and M stars, that kind of cuts it down to maybe a spread of 0.15 or so. Another thing you could do is observe a field of stars near the cloud and then determine the average color using color-color diagrams as shown on the left. And that's what's typically used in the literature. But what I was able to do is actually simulate a field of stars using galactic models to get an average color. And so you don't actually have to rely on a nearby field, which would possibly be extra observing time. And I also use the fact that my background stars are mostly late K and M stars. And so these are the particular clouds, I've already shown some of them today, that I was able to map with extinction. 4 of the 5 of these where I actually was able to detect ices for. These images were produced with JH and K band photometry on UCURT. So I have the photometry from that, and I also have the photometry from the Spitzer Space Telescope, the IRAC channels 1 and 2. And as you can see here, there's a very high density of background stars here, which is very beneficial because we can get a high spatial resolution of these maps. These are nearby, so you don't have contamination from a lot of foreground stars, and they're also fairly small in diameter. The top 2 here are these are collapsing cores, and the bottom 3 are star forming. So how do we make this extinction map? Well, what we do is along every line of sight, we're able to use that equation that I showed before, but extended for multiple wavelengths, to measure the extinction toward every star in the field. And so then what you see here, the cooler colors are actually low extinction, and then as you get to warmer colors, you get to a higher level of extinction. And you can see sort of in the center of the cloud here, you don't have a lot of stars in the background, so you don't have a lot of information in that center part of the core. But then when you smooth this into a map, you can actually see a little bit more about what's going on at the densest parts of the core. And so our typical resolutions range from about 13 to 30 arc seconds. And this is a major improvement from 2-mass measurements or 2-mass maps, which are on the order of about 3 arc minutes. So these are very high spatial resolution maps. And so this is what the extinction maps look like. I've also highlighted in some of these the lines of sight where we detected different ices. So this is basically, you can see the color image here, and then you can also see what it looks like in the extinction. So these are 2 more, and our last one shown here. There we go. It's a little slow. So then what I've been able to do is take these 2-dimensional maps, and using a mathematical technique called the inverse Abel transformation, I can reconstruct these into 3 dimensions. And so this allows us to measure the true density at a given point instead of the column density. So we can actually say, okay, at this point in the cloud, this is roughly what the density is, and this is where we're finding ice. So this technique that I used was an algorithm called Aviator. And it assumes that the distribution along the plane, along the line of sight is similar to the distribution in the plane of projection. So shown here at the bottom is what my 2D map looks like. And then once I do this inverse Abel transform, I get a central slice, just if I were to cut through the center of the cloud, and this is what I would see. And so I can understand what's happening at the center. And then if I basically reverse that process and I have the 3D map, and I integrate along the line of sight to produce a 2D map and compare it to what the original was, I find that the residuals are only on the level of a couple %. So it's doing a very good job at being able to produce this 3-dimensional map. And so this is kind of what it would look like in 3 dimensions. So what you would be doing is looking along the line of sight, and you usually see this is the total extinction, total A sub V. But then with this method, you can step through and say, well, what is the A sub V, local A sub V at a particular point? Well, A sub V at a particular point doesn't quite make a great physical interpretation. So what we can do is convert the extinction into a column density or a number of hydrogen particles using this equation here. And so we can actually say, as we go through the distance in the cloud, we can now get a volume density instead of a column density. And so what I've been able to do is measure what the peak density is where we see different ices. So on the top 3 plots here, this is sort of the profile if you were looking along the line of sight through the cloud and you were looking to see how dense it actually gets along that line of sight. You see that for the top 3 panels, this is where we're able to detect the CO feature with that extra red wing that indicated that there was a mixture of methanol ice with carbon monoxide. And these 2 figures on the bottom is where we were actually able to detect methanol ice on its own. And so you can see I've highlighted sort of what this peak density is, and it turns out that all of these have a peak density that's above 10 to the 5 per centimeters cubed. So we think that that is sort of the density that we would need in order for methanol ice to form. And so our density map findings, we had that we found that the maximum density reached in the core increases with evolutionary stage. So if you have a quiescent core, the density is actually lower in the highest density part than when you're in a collapsing core or in a star-forming core. So the star-forming core has the highest density. And however, we do note that the densest regions of our maps are the least sampled, so there could be a source of error there. The methanol or the CO mixed with methanol ice only forms above 1 × 10⁵ per centimeters cubed density in our sample. And these densities are reached in a very small part of the core, only less than 2% of the core by volume. So it's great, we now know a little bit more about the dust, but what if we could really map the ices in these cores? What if we could see, along every line of sight what the ice was for all of the background stars? Well, if we could do that, we would like to sample different stages of evolution so we can see how these ices are evolving over time and answer when ices start to begin to develop on dust grains. We'd like to go faint enough in order to sample very dense parts of the core. We can see how much ice exists at different dust densities and how much shielding is required for this ice to form. And we would like to cover a spectral range that detects all of the ices that I've talked about today, such as water, methanol, and this can help us constrain astrochemical models of ice growth on dust grains. And so our solution is the James Webb Space Telescope, as it is for many fields of astronomy right now, using NIRCAM slitless spectroscopy. So I'll go into that a little bit more. We have guaranteed time observations through NIRCAM team to do some of these observations to do exactly what I just said about detecting ices and mapping ices over entire molecular cores. And so we will do this at 3 different evolutionary stages. These are the 3 cores that we've chosen for our sample. We'll be able to observe these in 6 filters with a GRISM mode, which I'll get into what that means in a minute. And then we'll also simultaneously have short band photometry. So on the left here, I've shown the different band passes that we'll be able to cover, and you can see the spectrum here of a star or just with the ices shown that we would be interested in. So you can see that these filters cover some of these ices quite well. And the total observation time will be about 6 hours per target. That includes overhead times. So this is what the NIRCAM instrument looks like. It's made up of 10 different detectors made here in Hawaii, I think, or maybe not made here in Hawaii, but so it's basically made up of 2 long wavelength channels, and then you have 8 short wavelength channels. So the short wavelength are shown here in blue, and the long are in red. And it has a nice big field of view, very good spatial resolution. And there's 2 different modules shown here. So that's what the NIRCAM chip will have, are these 2 modules. And so this is sort of the observing plan, at least for B335, which is one of our targets, one of our clouds. So this is sort of how we will step through to cover the densest parts of the cloud. You can see this is an optical image, so it looks like there's no stars, and you're going, well, you're not going to get very many stars. But this is just to show that this is actually one of the densest parts of the cloud. And remember, when you go into the infrared, you'll start to see a lot of stars. So the way that slitless spectroscopy works is it basically takes every point source in the field and it disperses it into its individual spectrum using a grism. So this is also great because then we can also do these measurements and also get photometry at shorter wavelengths. The advantage to using slitless spectroscopy instead of using multi-object spectroscopy is that we don't need to have any sort of slit mask, which would require pre-imaging, which is also costly on James Webb. So if you were to use something like NIRSpec, you would have to have that requirement. And also on NIRCam, we have high spatial resolution. Another advantage is that we have the ability to dither the spectra across the NIRCam detector, which allows for better flat fielding. And as I mentioned before, you can simultaneously measure at long wavelengths and short wavelengths. However, the one disadvantage is that it's very difficult to use in crowded fields due to the possibility that spectra will overlap. So, well, I already told you that we have pretty dense background fields because we wanted to have a lot of lines of sight in order to measure ices. So I was able to produce this simulation to see what the spectra would look like for a given field in the 430 filter. And so on the bottom here is what it would actually look like if you were to get the spectra for all of the stars in that particular field at some amount of, including some amount of extinction. And so we wanted to determine how many stars had overlap. And so the criteria to determine this is that if only one star spectrum is found in a 5 by 1024 pixel box, then it should be safe. And then if there's a star that's more than 5 magnitudes fainter on top of your star of interest, then the star of interest should be okay. Or if the overlapping star is less than 1 sigma significant, then your star should be okay. So I wanted to see, well, will we actually be able to isolate enough individual stars well enough without significant overlap to measure these ice features? As you can see in the corners here, it looks like there's a lot of overlap, but in highest extincted regions, which I've already shared is where you're finding this methanol ice, it might be okay. So it turns out that we would expect about 100 spectra per cloud to be sufficient to study the water, the carbon monoxide, and carbon dioxide features. And many of these will also be good enough to study the shapes of these features per clouds, such as the wings in the CO feature where you saw that methanol ice mixture. And then on the order of dozens per cloud should be suitable for us to measure methanol ice and map the onset of complex grain surface chemistry per cloud. So I hope today I've convinced you that ice is a fundamental component in early star and planet formation, and it's a key phase to assist in the production of complex organic molecules. I've shared today how comets provide a window into the solar system's icy past, and 49P is a unique case study that demonstrates how a comet might be transitioning to a dormant state. My initial studies of ice abundances in molecular cores is the first simultaneous measurement of carbon monoxide and methanol ice outside of YSO envelopes. And we find that methanol ice, which is a precursor to complex organic molecules, is established well before stars form, and this shows that they form much earlier than previously thought. I have developed high spatial resolution extinction maps of dust in molecular cores, and then once I transform these into 3 dimensions, I find that only a very small fraction of the cores are dense enough for the onset of complex organic molecule formation. I've been an integral member in simulating our upcoming observations with the James Webb NIRCam instrument, and this will revolutionize our understanding of ice growth within molecular cores. And now I want to thank some of the people that have been essential along this journey. I really want to thank my parents, my husband, my sister. My sister was the one who actually introduced me to astronomy in the 2nd grade. She told me about black holes and I was hooked. Surprisingly, I'm not standing up here giving a defense on black holes. I would love to thank my committee members who have been extremely helpful along the way. I want to remember Don Hall, who is on my committee, and I'm really upset that he can't be here with us today. I would like to thank a lot of my collaborators. Many of these people supported me on my COMET work. Marcia Ricci and the JWSTINIRCAM team were extremely important in funding me and keeping this project going. I would like to thank for the different telescopes that I was able to use for this work, including RTF, UCURT, the UH-88, and the Spitzer Space Telescope. I'd like to thank some of the people here at the IFA who have really helped me along the way. These people are just essential to the IFA. Bill, Pam, who's here with me today, Susan, who's retired, Sandra, they've all been very wonderful in supporting me. I'd like to thank all of the people in the IT department, the time allocation committee for giving me the time that I needed and even a little extra time so I have some data to take with me on a postdoc. I'd like to thank the different people who have been the graduate chairs over this time, Dave Sanders, Jonathan Williams, and Karen Meach. I'd like to thank the Mauna Kea observatories, the directors that I've had over this time, including Gunther, Bob McLaren, and Mark Chun, who's here in Hilo. I also want to thank my fellow graduate class who were very important, and especially in those first couple years when we were all going through classes and quals and everything together. It was really a great team, and I'm super proud that everyone has gone on to do amazing things. So I'm very happy to be part of that class. I'd like to thank the Sir Optimus International Founder Region Fellowship for Women. This was a great opportunity. These people fund women who are in their graduate studies. So any of the younger students, please apply to this because it really is a special experience, and they think you're pretty much the coolest thing ever. It's a really nice treatment, and it's a monetary scholarship, and you know they really helped convince me to keep going, even when times kind of got tough. I'd like to thank my hula hula umanoa. They were extremely important to me as I explored Hawaiian culture. I feel like they also made me a better astronomer. They were always super supportive of me and loved hearing about my research, and even gave me a nice bouquet of flowers yesterday. So I'm very thankful, especially to my kumu, Kilahana Silv, who's just been there for me all this time. She even choreographed my wedding hula. The Summit of Mauna Kea has held a very significant cultural role for the indigenous Hawaiian community, and I'm very thankful to have the opportunity to observe from this mountain. I would also like to thank God for allowing me to unlock some of the mysteries of his creation. And finally, I'd like to thank my cat, Millie. She was there to provide many snuggles as I wrote my dissertation, and she was very helpful in keeping me calm. And finally, I just want to end on this note. And for those here in person, you can actually see I have this physical book called A Book About Planets and Stars. I got this in the second grade. As you can see on the inside cover, my name is written in crayon. So you can really tell how young I was when I first started getting interested in astronomy. The very last sentence of this book says, "Perhaps you will become a scientist, one who may discover even more wondrous things about the planets, the stars, and the universe." I'm getting emotional because today my dream has come true. So I'll leave you with my takeaways. Thank you.
Yay.
And now I welcome questions. I don't know if we have to unmute people. No questions. Great. I pass.
Well, people from the general audience would have to be unmuted. Of course, they can ask questions now. Then later the committee will go into a closed session.
Right. Let's see.
Okay.
Laurie, can I ask a question?
Yes.
Yes, Günther from Madrid.
Could you
Sorry
please?
for.
Sorry, could you share who's speaking?
Yeah, it's Günther Hosek from Madrid.
Oh, hi.
Hi, Laurie.
Hello.
It's very nice to see all of this and hear you. And I just had a short question. Do you have any chance to also look at the D/H ratio, the way the water is coming to the comets and to the star-forming clouds? Is there any diagnostics that can touch that?
So that wasn't really a focus of my work. I know that the D/H ratio is something that's pursued a lot, especially for cometary material, because we do think that maybe some of the comets delivered what we see here on Earth, what water we see here on Earth. As far as the D/H ratio in molecular cores, I don't think we can quite do that. But there's definitely a lot of studies trying to figure out the D/H ratio for comets, but we also don't know how much of the oceans on Earth have been altered over time. So it's kind of hard to even pinpoint what the D/H ratio would be early on and what it was for our early Earth too.
Thanks. And JWST will not be able to do that?
I'm not entirely sure. I have not looked into it very closely. I admit I'm not very knowledgeable on that particular feature, but
the water ice feature will be difficult because it's so broad.
Okay. Yeah.
We have been, or are looking into C12 versus C13 isotopologues, but the D/H ratio on the big water absorption feature is probably not resolvable.
Okay.
Okay.
Were you able to hear that? Okay.
Yes, thank you very much. Great.
Yeah, the HDO is actually at 4.0 micron. It's ideally suited for JWST, but it's broad. Yeah, it's not easy.
Any other questions? I'm not sure if people are raising their hand in Zoom or anything.
Hey, Laurie, this is Ben. Can you hear me?
Hi, yes.
Yeah, I have a relatively simple question. I haven't been up to date on the current launch schedule for JWST. So what's the current scoop on when we should expect this awesome work to happen?
Well, so I think they still formally have a date for March 2021, but I don't think that that's going to actually happen, especially with the pandemic. Best case scenario would maybe be sometime next summer. I don't know if she's on today, but Marcia Ricci was invited, and she said that they were doing all sorts of tests at Northrop Grumman on NIRCAM, and so she would maybe have to participate in different meetings on that. So I think that there's still a lot being done, so it's not like it's completely halted. But I would hope that within maybe a year or so, we'll be getting pretty close.
Well, that's optimistic.
That's optimistic.
Günther maybe knows more than I do, but the official launch date is still March.
I think the launch probability is a probability function that has a peak and a width, and I think the peak is somewhere around of October, but I think it's very uncertain.
A new schedule should come out this month or early next month. And the project manager has said to expect a launch next year. This is Tom Green.
Well, we can cross our fingers.
Awesome, thanks.
Okay.
Okay, I have a question. This is Yvonne Pendleton. Laurie, I'd like to know, what is the next thing that you would really most like to do based on everything you've learned from this thesis and your dissertation studies? What's the burning question or the object or the thing you most want to answer next?
Well, I mean, this kind of goes along with what James Webb will produce. I would love to be able to map these ices, but in the meantime, between when James Webb is launched and in the intervening time, I actually have some interesting data sets where I can probe a little bit more out on these outer edges of the clouds to be able to actually understand whether there, kind of understand a little bit more about the shielding. So in the lower density regions of our clouds, we don't necessarily have the best measurements of the extinction because the intrinsic color variation could actually impact our overall extinction measurement quite significantly. And so I actually have a lot of spectra of stars in the background where we can actually get the intrinsic color from spectra, which I mentioned was very costly, but I do have some spectra so we can understand these intrinsic colors. And this actually will allow us to understand a little bit more about how far out is this boundary of these different clouds. Another thing I also have going is I would like to, I have a kind of unique technique that I'd like to try as far as detecting water at a shorter wavelength in the K band. I could get into details later on that with you, but basically it would be kind of a new way for us to possibly be able to detect water and different ices and shorter wavelengths.
Wonderful. Wonderful. Thank you for that answer.
Mm-hmm.
Hi, Jamie. I have a question. I was wondering whether ALMA can give you any interesting constraints on these molecules or if it's not useful in this regime.
Yeah, so ALMA is something that would be very beneficial to look more at gas phase molecules. So these kinds of observations are typically looked at with like if you were wanting to study these complex organic molecules, a lot of these have been detected in the submillimeter regime in the gas phase. However, they're very difficult to detect in the ice phase. And so there's actually a recent study that came out that actually sort of said some of the same things that I found, saying methanol ice appears to be forming early on before a star has formed, but they were looking at methanol in the gas phase. And they have other molecules that they can also look at too that are more indicative of this onset of complex organic molecules. But as far as ice features go, it's a little bit more difficult to see those in that regime.
Thanks.
Mm-hmm. Any other questions? Okay. Well, if there's no further questions, you can always contact me over email, or I'm happy to meet with you one-on-one over Zoom if you're interested in hearing more about any of this. And I think now it's about time for my committee to ask me some questions. And I believe that means that everyone but my committee has to leave the room. So thank you very much, and thank you for your attention. I really appreciate having you all here, even though Zoom is a little different these days, but I really appreciate those who are here physically as well. Thank you for coming.
Thank you. Bye. Good luck.
Thank you.